Our next speaker is Sash Hier-Majumder from Royal Holloway down the road. He's going to be talking about melting above the transition zone. And take it away, Sash.
Thank you for that elaborate introduction, Dave.
Would you want more? I can.
No, that's okay. So, John and I talked a little bit about what the topic of my talk should be. And I'm going to talk a little bit. Typically, I work on small-scale structures, but given the scope of this specific week, I wanted to talk about large-scale distribution of melt. What I also thought would be good to kind of shift the focus a little bit. John and Mark did an amazing job of introducing the equations, and Mark very aptly ended with a question, where do we go with these calculations? So I'm going to try to show today that we could actually use these calculations and also coupled with some rock physics, theoretical rock physics calculations to address some issues. And specifically, I'm going to focus on the mantle transition zone or above the mantle transition zone. And the region I'm going to look into is the western US. So, of course, this is a work done in collaboration with many people that have not been mentioned here, but I am going to use quite a lot of the seismic data from Benoit Tozan. My two postdocs, one former now, Zhengyu Kai and Omyo Borua, and also this is a collaboration that had been ongoing with my former colleague at University of Maryland, Howard Ellman. Also numerous conversations with Dave, Mark, and John here, and Rich's group as well. So you will see bits and pieces of their work coming up every now and then. But one of the really crucial things when it comes to the transition zone is understanding the role of volatiles. And when I talk about volatiles, I'll focus mostly on H2O and CO2, and a little bit more on CO2 later on into the talk. So it might be helpful to just kind of have an idea of what are some of the abundances and fluxes of these volatiles in the mantle. So just some numbers to keep in mind. So I looked up some references to find out what are the estimates of how much water and CO2 we could have in the Earth's mantle. So for water, we have an estimate of between 1,000 to 3,000 ppm H2O in the rocks. That's a lot of water in the upper limit. If you have 2,700 ppm, that's about equal to 10 oceans worth of water in the mantle. Okay, probably a little bit more realistic estimate would be about 3 oceans worth of H2O. So when I say an ocean, I refer to this number, 1.6 times 10 to the power 21 kilograms in terms of H2O. That's the near surface abundance. Carbon is a little bit less abundant near surface. So you can see this is around 9.3 times 10 to the power 19 kilograms. Okay, so what that means is if we just take, and this is Mark Hirschman and Raj Dasgupta who kind of forwarded this idea. If you look into the H over C abundances in the Earth, what you find is quite interesting. Near the surface, this ratio is 2, but for the bulk Earth, the ratio is close to 1. What that means is in the mantle, we must be storing carbon, or in the deep Earth, let's say, we must be storing carbon in greater quantities than we see on the surface. Okay. Now, we could also look into sort of this ballpark numbers, and this is a number I'm going to come back to later, so worth keeping in mind. If you take a look into how much carbon goes into the mantle of the Earth, and how much of that comes out by volcanic degassing, you can come up with this sort of net amount of 3 times 10 to the power 16 kilograms of carbon per million year going to mantle. Okay, and that's after taking out that 40% to 70%. And if you also did a very, very simple residence time analysis, what you would find is the residence time of carbon in mantle, just based on these very simple calculations, it's approximately 1 billion years. So there has to be some repository somewhere, and it has to be relatively long-lived. Okay. Now, it's also worthwhile pointing out The two most abundant volatile species that we talk about on the Earth, carbon and hydrogen, they have very contrasting behavior when it comes to the transition zone. Okay, so let's look into the hydrogen case. Dave and Shun came up with the idea of the transition zone water filter model, which was primarily based on the idea. If you look into, I preferred the term solubility over storage capacity, but if you look into the solubility of hydrogen in nominally anhydrous minerals, this solubility picks up quite a lot in transition zone. So as a result, if there is a upwelling or downwelling of the transition zone, around the transition zone, you could potentially move minerals that are oversaturated with water, and they could release the water, causing dehydration melting. So a couple of the examples are shown in this cartoon here. For example, if you have a plume type situation, then upwelling would cause this oversaturated rocks to come up above the transition zone and could induce dehydration melting. And you could see the similar behavior at the bottom of the transition zone with subduction that could again cause dehydration melting underneath. There is also actually Guillaume, Dave, they have done quite a lot of work in, they have done quite a lot of work in terms of what happens with the very thin hydrous molten layer near the subduction zone. I'm not going to get into that very much. But one of the interesting things is when you look into the carbon behavior, it's quite different because of the fact that carbon has a much lower solubility in mineral phases. Okay? So just the way we can take hydrogen and we can look into the differential solubility of hydrogen within the nominally anhydrous minerals, it doesn't quite work that way with carbon. Okay? And what makes the case even more difficult to understand carbon is the melting of carbonate phases, or even the stability of carbonate phases, depends very strongly on the oxygen fugacity of the mantle. And typically it's believed that the mantle is quite reducing, so it's very likely that carbon could exist in one of the other states, like as a carbide phase or diamond or graphite, something like that. But one of the points to keep in mind here is if we are looking into the subduction zone above the 410 kilometer discontinuity, we are actually moving minerals that have some amount of hydrogen, let's say, but we're moving them into a condition of undersaturation. So if it's just what sort of volatile release is taking place here, you're probably not going to see a lot of dehydration melting up there. And also it's worth mentioning that in the upper 150 kilometers or so, the nominally hydrous minerals in the mantle, in the subduction wedge, could get quite efficiently dehydrated. So, so basically, this is sort of a modified version of the transition zone water filter model cartoon. This is from a follow-up paper that was led by Shankarado. And this is a figure from Brandon Schmant and others' work that came up in Science a couple of years ago now. What they found was that in regions of downwelling, there was this low amplitude anomaly of PS to P conversion just underneath the 660 kilometer discontinuity. And they concluded that this is probably happening because of the fact that it's the effect of downwelling slabs that's causing dehydration melting at these depths. Okay. We do know that the water in the transition zone could exist, and there could be quite a lot. In fact, this is one of the recent discoveries I was quite psyched about, the direct observation of hydrous ringwoodite inclusions in ultra-deep diamonds. So these ultra-deep diamonds actually generated in the transition zone depth. Okay, and I'll show in a second later on why, in the next slide, why diamonds play such a crucial role, because of the fact that they have a lot of indication that they actually were formed in a carbonate and a carbon-rich and hydrogen-rich fluid, and that's why we know that this hydrous ringwoodite does prove that there is at least in some parts of the transition zone, there is quite a lot of water. Now, ultra-deep diamonds could tell us quite a lot also about the state of carbon in the mantle. Okay? And I'm showing this example from the work of Bulanova et al., where they were looking into a series of diamonds from Brazil. And the summary of these observations is that they found, based on carbon and oxygen isotope signature, there was sufficient signature to say that these diamonds were actually derived from material that was originally on the surface, or in other words, they have a source that you can link back to a subducting slab. Diamonds also have a very specific crystal structure, and the structure of the diamonds often indicate that they actually crystallized from a melt rather than a subsolidus reaction. In this specific suite of examples, what they also found was quite interesting. If you look into the composition of REE, the rare earth elements, these diamonds have quite an elevated level of those elements. Okay? What that typically means is these diamonds must have formed from a very early batch of melting, or the source of that diamond, the melt that was at the source, must have been quite small, and as a result, all of the incompatible elements partitioned into the melt at a high concentration, and that's what you're seeing in here.
How high?
Hmm?
How high?
You know, I don't quite remember the values, but these were, I think, a factor of a few, 3 or 4 maybe. Yeah.
The partition coefficient is diamond, which I don't think we know.
Right.
No, if you're saying I'm trapping a small melt, trapping it, then I'm just curious. If it's,
You're not trapping though.
no, you're growing it from it.
It's growing it from the melt. Yeah, it's not an inclusion, sorry. And the other thing about these diamonds were also, there were some barometric models of the inclusions that seem to indicate that they were originating at depths greater than 10 GPa, or 300 kilometers or deeper. Okay. So, now, there is a very interesting article that just came out earlier this month, and this is from Mike Walter's group. And what they did was basically they tried to bracket the melting curve of carbonates, but carbonates that have a relatively close bulk composition to the mid-oceanic ridge basalts in the IODP samples. So these had about 2.58% CO2. And what they see is quite interesting. So pressure is here, unlike the depth way. The pressure is increasing on the x-axis here, and temperature is going up on the y-axis. I'll show another version of this figure in a little bit. But what you see is quite interesting, that there is this very sharp ledge in the solidus. Okay? And they attributed this ledge to the formation of very sodium-rich carbonate phases. So it's a subsolidus reaction that happens at these depths, and that subsolidus reaction pulls the solidus down. And the geodynamic consequences and consequences of melting of this behavior is quite interesting. So basically, if you're bringing in the slab that has a substantial amount of carbon in it, the carbon could probably survive parts of the dehydration that happens at the lower depth, 100, 150 kilometers or so. But as you get close to the transition zone, you're getting pretty close to hitting this ledge. Okay? And especially if the slab is relatively young and relatively warm, they estimated you can melt up to the top 7 kilometers of the slab and extract the carbon out of it. Okay? So you could create a carbon-bearing melt right on top of the subduction zone by this process. Okay? So that's just sort of the background that we're going into it. And what I want to do next is to show how we could use some seismic observations to quantify, is there any melt in some of the regions of observation. And then in the next part, I will show some of the two-phase flow models. So let's get into the seismic observation. A lot of this is work of Benoit Tagent. So some of the earlier data came from Benoit's work in 2013, and what he did was basically looked into the amplitude of P to S conversion at this reflector at 350. And typically the amplitude of this P to S conversion was about 50% of what the amplitude was of at 410 kilometer. So basically what that means is in these regions, because they don't directly measure the shear wave velocity, they measure the amplitude of the conversion. But when you back calculate that, you get ballpark 2% reduction in the shear wave velocity. So, so this is showing the study area. This is the Western United States. Now, I want to tell a little bit about the analysis that's done here. So, first of all, in this type of receiver function studies, you could get quite a lot of information. You could get the amplitude of the different reflectors. You could also get the depth to the 410 kilometer discontinuity and depth to the 660 kilometer discontinuity. And often it's used to the, with the fact that these are temperature dependent phase transitions. So the depth at which these transitions take place controls the depth of 410. So if you knew the Clapeyron slope of the reaction, then you could actually pinpoint the temperature at that depth. Or better yet, what you could say, if I see a deviation of the occurrence of 410, that is 410 does not appear at 410, it appears slightly shallower or slightly deeper, you take that deviation and convert that into a temperature anomaly using the Clapeyron slope. Now, this type of analysis has quite a lot of uncertainty that could come from the actual magnitude of the Clapeyron slope itself. Benoit and Yannick wrote a paper earlier on several constraints. I think Christine Hauser had a paper, and myself and Anna Courtier and Ellen Kill did some analysis also. So for this, our preferred Clapeyron slope is 3 MPa per kilometer for the transition at 410. Okay. Kelvin, sorry. Not per kilometer. So basically what you're looking at here is this is the temperature anomaly that's calculated from the depression or variations in the 410 kilometer. This is the map of the amplitude of the 350 kilometer. Now, one of the things that you could see here that there are some patches where we have really sharp drops in amplitude. Okay? And the other part here is we're looking into the thickness of the low velocity layer. If you look across this transect here, there seems to be a relatively lower thickness away from the coastline. Okay? So it's almost like this layer is tapering off, but you probably have to squint hard to see that sometimes. The other point I wanted to make in this figure, since we have the actual plots of the data points, we don't have a lot of data on Nevada and California, and that has to do with just that the signals were too noisy here. So just keep that in mind. So we can compare these observations here. What you're looking at, again, two transects. This long one here is on the left, and the shorter one on the right. And we're comparing that at the bottom with P-wave tomography results. Okay? And some of the things that comes out of the P-wave tomography, the star here is the Yellowstone. And I think the Yellowstone caldera is somewhere here too. So we have this Gorda plate, which is this sort of blue phase here, and we start to see the edge of the craton. And then on top of that, we see this region where we have somewhat of a lower velocity. And we see some variations in the thickness of the transition zone. It thickens and becomes thin. The 350 kilometer discontinuity is this light little blue layer here. Okay? So it's persistent for parts of it, but in some other parts you don't really quite see it. So let's see if we have a zoomed in version of that. So now we are looking into this transects again. So AA is up here, and BB is this profile. So you see the top of the 410, and then 350 is marked right there. Okay? And what Benoit did was he tried to calculate the thickness of the 350 layer along the profile. Now, again, the signal is not perfect for for the left here near the near Nevada. We don't have a lot of data, but as you go towards the east, you can see that there is some decrease in the thickness. So those are some of the observations we are getting from this seismic profile. What we wanted to do is not just take that delta Vs or amplitude value and say, oh, there is melt. We actually wanted to try to calculate that. Okay, and I used this code MuMap that I wrote some time ago. It's multi-phase material properties. What we do is basically we just use this very simple type of idea. We have the observed values of the shear wave speed. We choose a reference shear wave speed, and for that we use the database of Shu et al. This reference speed here depends on the bulk composition of the solid and the temperature at the location. Now remember, we do measure the temperature at each location based on a reference potential temperature and then the temperature anomalies for that. So this guy actually varies between each station based on the temperature. We consider the bulk composition to be constant. And then we define this melting anomaly function, and the melting anomaly function really tells you how the melt would actually influence the shear wave speed reduction. I'm going to show the equations in a second, but just schematically, there are three things that can go into this function. The first is, of course, the volume fraction of melt, which is an unknown we're going to solve for. The composition of the melt, which controls the density of the melt and the bulk modulus and things like that. And also the dihedral angle theta, which controls the contiguity or what fraction of the grain areas are contained there. Okay? So if we write this down, basically we're looking at solving an equation like this where the observed Vs minus the reference Vs times the melting anomaly function is less than some preset tolerance. Okay? And this is a relatively benign looking function formulation of this melt anomaly function. Now, even if I say it's relatively benign looking, but it's not really, because this guy, psi here, is contiguity, which is again the fractional area of grain-grain contact. That's a very strong nonlinear function of the melt fraction itself. And this exponent n here is also not a constant. It depends on the dihedral angle and it depends on the contiguity itself. It comes from Yasuko's work, actually. So what we have here then is a system of a set of nonlinear equations. Okay? And what we do to calculate the melt volume fraction at each point, we solve these nonlinear equations at each station. Now, in terms of solvability, the matrices are actually quite well defined because we have a perfectly diagonal matrix. We don't have contribution from one station to another. So as a result, the code is extremely fast. We could run this analysis for all of the stations on a laptop, and it takes only like 3 seconds to calculate. So it's really quite, once you get that done, you can choose your parameter. You can say, this is my mantle, this is my mantle's temperature, this is my mantle's composition, this is my liquid, this is the dihedral angle of the liquid, and it will spit out a melt fraction for you. Okay? So this is the volume fraction of the melt, the map that's calculated from the observed anomalies. I just wanted to point out that, again, I wouldn't pay too much attention. This is just interpolation of the data in the plot, so we actually don't have any calculations here. But what I would say is that if we take a look at this representative case here, the maximum is 3 volume percent melt and the minimum is 0. What we see is that there is sort of this broad region. This is where our data is the most dense, both of these regions. We see almost a decrease of the melt fraction from almost this linear streak. Okay, and that kind of matches the patterns we were seeing before with the thickness of the melt volume fraction. So this is quite exciting actually, because when we look into the overall regional average, we get on an average about 1 volume percent melting here, and that's the regional average, and then we get some highs and some lows. Okay. As I mentioned before, when we try to take this melt fraction and plot that, the thickness of the melt layer as a function of melt fraction, if we take all the bins, we don't really see any visible correlation. It's kind of all in a big jumble. But once we go into this type of transect again, we see some sort of correlation, and we haven't quite finished analyzing this correlation of measuring the melt content along this transect yet. But at least visibly there is some sort of trend. Okay. So this is just showing the density of the stations from which we got the data, the melt volume fraction. Now, MuMap also has a forward modeling tool, so those of you who are interested, I'm very happy to share that. We could forward model the electrical conductivity once we know the melt fraction. We could also forward model shear wave speed. So that's what we are looking at here. And this is the bulk conductivity for a CO2 and H2O rich peridotite fluid from the work of Cifre et al. And what we find here is that if we look into, for that type of melt fraction with a carbon dioxide and H2O bearing fluid, we get a bulk conductivity on the order of about 0.01 Siemens per meter. Okay. The results are not completely out of the whack, because there are at least 2 other places where I have done this type of analysis. Anna Courtier and I looked into the Coral Sea area in Australia, and more recently we have also done this type of analysis in Hawaii. But in neither of these places we had as much density of data as to produce a map. So this is the first time we have this type of data because of the US array. But in both of these regions, given their temperature variations and things like that, we did come up with that ballpark 1 volume percent melt. So at least our estimate of melt is relatively similar to these 2 different regions. If we look into the electrical conductivity, that becomes a little bit difficult, because these are relatively large depths to measure electrical conductivity from. So these measurements are quite difficult actually. But there are a couple of constraints that we can have. So there was a paper by Lizarralde et al. Where they measured a quite elevated spike of electrical conductivity in the North Pacific right above the transition zone. And their conductivity was actually higher than what our average is, about 0.01. There's also some more recent work by Shimizu et al. And quite a few other ones on the western coast of the Pacific, and they come up with a slightly lower estimate. So theirs varies somewhere between 10 to the minus 3 and 10 to the power minus 2 conductivity. Okay, but again, given the differences in the regions, at least what we are getting out of this electrical conductivity forward modeling does seem to match not too poorly with the observed values of the electrical conductivity. So, with having done this seismic observation and having this sort of backdrop that I told you about in terms of the global budget of the volatiles, I want to talk just a couple minutes about what could be the origin of this low velocity layer. Now, I'll come back to this. I'm coming back to this picture that I showed before from Thompson et al. And this was another figure from their paper. So this is probably a figure we are going to see a lot in the coming years. But basically, this is the solidus that they calculated. And they also, now we have temperature and pressure on this axis. You could also see depth, 300 kilometer and 410 is here. If you have a relatively young slab, the hot slab surface and the hot slab moho, they can intersect this solidus quite far above the transition zone. And that was the whole idea behind this work. And if you look into the paper, their argument in that paper is that this melting could serve as a barrier to deep carbon ingassing because of the fact that you can get rid of a lot of the carbon from the slab by this process above the transition zone. So the carbon might actually be sequestered in the upper mantle, okay, or a majority of that. So what I wanted to try next is, having gotten a handle on what the background volume fraction of melt is in this area, having this sort of idea that we could actually induce melting by the presence of volatiles on top of the transition zone, I wanted to see what are the dynamics of that. Now, there are a couple of additional factors that we need to consider. The first factor is what's the density contrast, as we have seen in both John and Mark's talk. That plays quite an important role. So one of the information comes from this work by Sujoy Ghosh, and what Sujoy did was basically he calculated the density of peridotite melts with different concentrations of H2O and CO2. And what he found is that carbonate-rich peridotite could become nearly neutrally buoyant or even denser than the mantle at the transition zone-like depths. So if you are able to create a melt, the melt is not necessarily going to try to rise just because it could be stable down there. Now, the question then is, what happens to this melt? Does it drain out to a very thin pool that we can never detect seismically? Now, we need to remember that this is in a state of flux, so we are getting constant background flow coming from the subduction zone and probably the metasomatic reaction of the melt with the mantle. So what we want to try to see is, how about in a time scale of maybe 5 to 10 million years, what happens to that layer? And also, what can we say about the global carbon cycle that we talked about earlier? So I'm going to show the equations very briefly. It's the two-phase flow equations again, so slightly written again slightly differently. But here we have this operator. This is the symmetric gradient operator on velocity. We are solving this for the matrix velocity and what I call a reduced pressure, which is the fluid pressure and the lithostatic pressure taken into it. Okay, and unlike the bulk viscosity term that Mark uses, I prescribe that slightly differently, so that makes my equations look just a tiny little bit different, but not that different. The other thing I do is also, instead of just doing a pressure velocity formulation, I break it up into three fields, a split field formulation. So Mark and Kian came up with that, and then Rich and his postdoc Sunder has done some remarkable work on this area, showing that there is a lot of advantage in terms of increasing the scale of model, because you can converge on the iterative solvers quite quickly, even if you're increasing the degrees of freedom in your problem. So we have this action-reaction equation, as we like to call it, but it is a version of the momentum conservation equation. These are linear equations, so you can add or subtract. This guy H here, if you want, I can talk about it later, but it has in its surface tension, density, buoyancy, and melting. And then we have a modified version of the Darcy equation. So again, I use the length of the box as the length scale, but as John pointed out and Mark pointed out, compaction length is the natural length of the system. So you would see this ratio pop out somewhere. And then we have this melting term that occurs in this equation also. And finally, we got this substitution of the scalar compaction. One thing I wanted to point out here is that I have a minus sign in front of this. I think both of you guys didn't have the minus. So as a result, what I call compaction is your decompaction. Okay, I'll come to that in a second. And then this is our mass conservation equation. Worth mentioning that if we forgot melting for 1 second, then d phi dt would be positive. Just let's also say for now, melt fraction is constant also. D phi dt would be positive if this divergence of u term was positive, or in other words, C was negative. Okay, so just to keep that in mind, because I'm going to show some structures later on. So when I discretize these equations, they basically end up looking like this block diagonal system. I don't know why I put that B up there. I'm sorry about that. It shouldn't be. So that B should go down there. Very sorry about that. So basically, we have this system, and we have the velocity U, the pressure P, and C is the compaction. Those of you who are used to looking into the one-phase equation for the Mantle convection, you would probably recognize the equations look kind of similar, but a little bit different, because for Mantle convection, we got A, B transpose B, and 0. And this guy down here causes a lot of trouble. And we don't have that in two-phase flow because of the fact that that comes from the Darcy equation, which is kind of a nice feature. And then both Rich's group and Howard and I have spent quite a lot of time, and Mark as well, in trying to find out what's a good preconditioner for solving these type of problems. I think it's still a work in progress. But I'm using this type of block diagonal precondition that Sander Raybergen proposed in his recent paper. Okay, so we did a couple of test cases. I'm going to show a couple of quick movies, and hopefully it will work. The first case is a 3D soliton. So we took the analytical solution, like Mark just mentioned before, from Gideon Simpson's work. And again, for these test cases, we don't have any melting or surface tension. The soliton is negatively buoyant, and we put a periodic boundary condition at the top and the bottom. And then I'll also show a case of a rising diapir, which is basically what you would expect to happen in a pipe with a perturbation at the bottom, and it's buoyant, and how it rises. And we again put periodic boundary condition on the top and the bottom. So this is the soliton solution. What you could see here is basically this red is the isosurface of 17 volume percent melt. So this is a relatively high volume fraction soliton. And you can see these two very distinct lobes of compaction and decompaction. These things come up again and again when you do the 1D analytical solution of the soliton. You can see this type of behavior, that in front of the soliton you're actually increasing the melt fraction. So what you have is what's my negative C, and you're draining out the melt at the bottom. So you get this little red lobe at the back. And because of the fact that this is a particle-like wave, you do have this very localized behavior. If you see in the background, everything is 0. So the map here is of that compaction. And this is the map of melt fraction. Okay. And this is the test case of the diapir. Again, we are showing the compaction and the diapir rising through. That was an isosurface of 0.17. I'll try to run this one more time. So you can see that there is this, again, little mushroom of decompaction that forms ahead, which is basically the region in which the diapir is draining the melt, and it's rising up. So these were just a couple of test cases. I wanted to get to our problem. So we started off with a relatively simple 2D problem, so we didn't go into 3D quite yet, but we have a 2D wedge, and we prescribe a subduction velocity on the slant side, no velocity at the top, and the box height is 410 kilometers and 820 kilometers across. We do have finite surface tension in this, but that doesn't really do much. In fact, if you guys want me to talk about surface tension, I can talk about that later, just to show you a couple of results from linear stability analysis. We also have a spatially varying melt fraction. So the idea is that we want to simulate the effect of melting because of carbon at the base of the wedge. And we also apply that spatial melt density gradient based on the work from Sujoy Ghosh. So these are prescribed functions. So this is gamma that we have talked about before. So it generates melting right at the intersection between the slab and 410 kilometers. And we have this density contrast, which has this sort of tanh-like function. We have a decreased density near the bottom. And in this specific case, it's actually quite exaggerated. The melt is up to 60% denser. I just wanted to crank that knob a little bit high to see, does that make the melt completely flatten out? So what we are seeing here is a simulation that takes place over 12 million years. On the left, we have melt fraction, and on the right, we have compaction and the streamlines of velocity. What happens is, as you see, the melt starts to generate and starts spreading like a gravity current-like manner, very similar to what Neil showed us yesterday, just upside down. And what that does is it influences the flow field in the matrix. We kind of get this little circulation cell there. And this front keeps advancing relatively slowly over time. Okay. So again, here the maximum melt fraction is 2 volume%. That's where I'm saturating this. And we get a background melt fraction of a half volume%. Okay. Again, we can do some forward calculation of physical properties. So again, this is in a coarser grid calculation. This is the melt fraction. We can get the contiguity for the entire domain from that. We can get the electrical conductivity, which is again in the same ballpark that we are seeing, and we can predict the Vs over V0 as well. So when we take these results, some of the things that we are seeing over this 12 million years that we have looked into, the melt layer does remain seismically detectable. So this is going from 0 to 12 million years again for your information. The average melt fraction in the layer does remain in the 1 volume%. Rich?
When you're finished.
Okay. Okay, sure. And we did a very rough calculation of the spreading velocity of this melt front. So if you will, like Neil was showing the other day, when you have a spreading gravity current, what you want to do is you want to measure the flux across this gravity current. So we just numerically tried to evaluate what this spreading rate of this current was, and we come up with something like 15 kilometers per million year. And again, the forward modeling electrical conductivity still stays in the same ballpark. Go on, Rich.
So I see what you're getting at is that, you know, that layer remains thick enough to be seismically detectable. And maybe I'm wrong about this, but it would seem to me that that will depend very strongly on two things. One is the boundary condition. Is the bottom of the box permeable or impermeable? And secondly, what is the compaction length along that?
So
if the compaction length is large, then the layer will remain nice and thick, and if it's small, it will collapse down to something of the order of the compaction length.
So
talk about what you've done
sure,
for those two things.
Sure. So the compaction length, let me just get back to this here. So the compaction length is 1% of the total length of the box, so it's relatively small, but not too small. I mean, it's about the length scale of the layer. It's 40 kilometers-ish. Four, sorry. And then for the boundaries, we prescribe velocity on those two boundaries. The remaining boundaries are basically like what you guys call the stress-free boundary condition in your case. So which is what's happening to the bottom boundary here.
So melt can percolate out, or it can't?
It can't, but you wouldn't also expect that necessarily for the 410 because you are.
Reversal in density contrast.
So the density contrast for the melt, basically, let's say you have the melt generate at top here, right? And just in this case, because if you are not generating melt down there, it doesn't really have a way to go down into the 410 kilometer.
It's impermeable because there's no melt beneath it.
Right.
Would it freeze?
But
There's a
it
reversal
could be
of the density
advected.
contrast.
It could be, and it is.
Did you say the
What we're seeing, though, it's advected sideways more than advected downwards. But you're right that could be because of the fact that my sample is bottoming out here, my domain is bottoming out here. So that's almost forcing this lateral advection, and that might be pulling it to the side.
You made the melt
Compaction length is so small,
Mm-hmm.
then why is your layer of melt so thick?
Because I'm generating melt. So I have a gamma term here, right? That's non-zero.
You made the melt 60% denser than
Yeah.
ambient mantle?
Yeah.
first of all, that would be denser than the transition zone, and it would
Right,
through.
right.
And secondly, I mean, that's an insanely large.
It is, but the
That
idea,
all is unreasonable that it's not thinning out to an infinitesimal layer with that density contrast.
right, the idea there was that I really wanted to tweak the knob, and what's happening is, here is the primary reason. Even if you have a relatively large density contrast, there are two things to remember. The first thing is that the melt volume fraction is still quite low, which means your permeability is still quite low. So as a result, the gravity wants the melt to drain into an infinitesimally small pool. On the other hand, the matrix is trying to advect it away. And it turns out, just for these type of melt fractions, you would actually have that the matrix advection time is smaller than the gravitational settling, so it could not essentially drain out. What I have, I actually have a linear stability analysis for that in a slightly different way, but if we were to go up to a higher melt fraction, say 10 volume % melt, I don't think we would see this same type of behavior. I think we would see the melt drain very quickly. In fact, we have that exact same problem for the ultra low velocity zone at the core mantle boundary, where we think the melt volume fraction is quite high, about 10 volume %. And John Herland and Paul Tackley did a paper where they showed that there is just no way you can have that much melt be stable over, like millions of years. It drains out very quickly. But my argument here is primarily the issue that we are seeing is because of the very relatively low permeability, because the melt fraction isn't really very high, even if it looks quite large. If that makes any sense.
Well, it's usually about permeability. Sorry.
So your compaction time is long.
Yeah, exactly.
Essentially,
How low, two questions. One, the compaction length depends on a reference porosity. What's that?
True, but that reference porosity is not the background porosity. So what we do here is basically, well, actually it is about the same. Yeah.
So that's the compaction length in the thing, but to propagate into you're starting with something with zero porosity off to the side, so there's an issue how you actually propagate. It's the compaction length, the thing that controls the size of the waves is the compaction length in the small region, and that's probably not being resolved, which is
True.
how we're not seeing some of the waves.
True, but that's exactly the idea too, right? We want to see the problem in the larger setup, not just what's happening within the compaction length scale. So what would give us
Resolve the small one to get the large scale structures. That's the problem, because it's dispersive. You don't resolve the boundary layers, and you get that. Yeah. Well, it's unclear, but and then the second question, which is I missed your. So there's really two parameters in this. There's delta on L, and there's some melt velocity on the solid velocity.
Yeah, solid velocity. There are a couple more actually. I haven't shown all of them. There is also the Dam-Kohler number, and then there is the the density contrast I did show.
But the one that would help a lot is just sort of reference melt velocity to solid velocity. How advective is that problem? How low is the permeability?
So I don't have the so in this specific case here, I think the magnitudes are quite comparable. I didn't have for the melt velocity and the solid velocity. Any other questions?
Melt velocity relative to the solid, or the melt velocity?
Sorry, the percolation velocity. You just said
The percolation velocity is quite small, so the melt does not segregate from the solid
melt
quite
is just being
effectively.
carried by the solid.
Yeah.
It's just advected.
Yeah.
Very impermeable.
Yeah. So,
If the melt, if the melt isn't moving relative to the solid, then why are you using a compaction equation?
we want to see
Okay,
that
then-
happen because of the equation.
But
It's order 1, it's not 0.
no, well, two things. I mean, is it of the compaction velocity? You said is essentially zero.
Compaction is small.
Percolation velocity, yeah.
The percolation velocity.
Percolation velocity is essentially zero.
Right. But we are not. We want to see that come out of the problem naturally, rather than imposing that and not using the compaction equations. So what does that mean in terms of transport of dissolved carbon? So we just did again like a very simple back of the envelope calculation, if you will. So we took, on an average, if we take the front advancement rate that we can get from our model, 15 kilometers per million year, it can change a little bit based on like off the boundary conditions and other things. But if we take this 30-kilometer layer that contains about 1 volume percent melt, and if we assume this 508% carbon and the melt density 3,400 kilograms per cubic meter, and we take a length of the trench 2,000 kilometer, we get up to 2 times 10 to the power 15 kilograms per million year of carbon. Okay, so now remember the global subduction influx of the carbon is 3 times 10 to the 16. So what we could say about a layer like that, at least we can get several tens of % of the carbon that's coming in through the trench that can actually go and be sequestered in this layer. Okay. So there are a couple of things where I think it will be really, I wish Mark had a little bit more chance to elaborate on the reaction infiltration instability, because one of the really crucial parts in sort of the large scale picture of this is these carbon bearing melts are also supposed to react with the mantle quite fast. So what I have here is, well, I have a reaction that's generating the melt, but I don't have the reaction which causes the melt to freeze or create carbide phases or diamond and things like that. So that's definitely an area worth looking into. So it could very well be that you may generate almost a layer that freezes almost quite instantaneously, but then you keep piling melt on top of that and propagating farther and farther. But the observation still does remain that we do see the melt at some distance away from the intersection between the slab and 410, what means that the melt has to transport some distance. So I'm going to leave with this sort of idea, basically based on the idea that the dissolved carbon and dissolved hydrogen interact differently with the transition zone. What that means is the transition zone could almost work in a different way. I'm not going to use the word filter. It called it a demixer. But basically, the transition zone could act as an area that separates out carbon from the hydrogen. So because of this decarbonation melting, you could get some amount of carbonate-rich fluid on top of the subduction zone, which is what we are seeing in these low-velocity zones. And because of the dehydration melting just under the subduction zone, and maybe some redox melting also of the carbon that survives, we can see another molten layer at the bottom of the transition zone. This is what Schmandt et al. Reported. So that's just something to think of in terms of the global volatile budget of the carbon. And just basically the idea of this type of analysis is that we want to take the different types of tools. We can take the observations and not just, we can actually quantify the outputs of the observations and then use our this type of models to actually get some numbers out of it. So anyway, I'm going to stop there and take any other questions.
So I think, oh, sorry.
Go ahead.
Sash already pointed at me. So I think that what, if you combine the modeling that you've done with the seismic observations and the interpretation of 1% porosity, I think what it shows is that if that interpretation of 1% porosity is right, then the permeability is remarkably low given the size of the porosity.
Mm-hmm.
Because if it was like the asthenosphere, if it was like the upper part of the mantle, the melt would drain.
Mm-hmm.
So the question,
But over how
the
long?
question to you is there something special about these materials and these conditions that would lead to de-wetting, large dihedral angles, lack of connectivity of the melts, or would that screw up the seismic observations? Because otherwise they don't seem to fit together.
So the dihedral angle is expected to be quite low there, okay? And the fact that the dihedral angles are low could also, in the small scale, prevent the melt from draining, and it's quite counterintuitive. Every time I say that, people go like, what? Well, here's the idea why. The small dihedral angle means it's a more wetting fluid. So think about a plate of glass and you put a drop of water in it and a drop of mercury in it, the mercury does not wet the water and it's very glissant. You tilt the glass and the mercury will move around. But if you tilt the glass, the water will have a harder time moving because it's a wetting fluid. It also has a higher surface tension that makes it stick more. Okay, and that's essentially what when Dave, Yannick, and I did this work some time ago now, almost 10 years ago. What we found that the dihedral angle, the lower dihedral angle, really does make a difference in terms of the surface tension and drainage, as does the melt fraction. I'll just show one slide.
So that H term of yours is what's responsible for this, not the choice of low permeability?
No, I think it really is the permeability, and the permeability is just like tubes, you know. So it's just the permeability of the standard formulation. So what I just wanted to show here, what surface tension does, please bear with me, this is a 3D linear stability analysis for a simple shear case. So basically, if we had in a perturbed state, this is a case where we're doing some shear, it doesn't matter so much as what we are looking into, but the contrast between the two cases. So we have a melt perturbation, or background melt fraction, and then a wave-like perturbation in 3D. And what we're doing here is we're looking at the growth rate S here as a function of the wave vectors kx, ky, and kz. I would like you to focus on this side of the plot. So the bond number is 100. What that means is surface tension is finite here. Okay? And what we see is, in this case, we have a background melt fraction of 1 volume percent, versus here we have a background melt fraction of 30 volume percent. And what happens at the 30 volume percent melt fraction is the melt wants to self-separate, just like oil and water, because the contiguity is lost. So the melt and the crystal, they want to separate out. The drive from the surface tension is that way. Whereas for lower melt fraction, the melt wants to homogenize. So if there are disparate pools of melt that are connected together, they will try to even out almost in a diffusive manner. But what's really interesting here is the values here. If you look into the growth rate for the higher volume melt fraction in the self-separation regime, well, you do see these changes in color from negative to positive because of the change in behavior, but also look into how different the magnitude is. That's because of the fact that at high volume fractions, the processes happen a lot faster because you have all of the other additional factors that are helping the melt to drain out. Whereas at the low melt volume fractions, you are not necessarily, things are not growing or decaying as fast as they would at the lower melt fraction. Okay, so I have another question, John, can I take it?
I just wanted to check something about melt densities. So in Andy Thompson's experiments, I think the melts he was making were carbonatites.
Yeah.
But
I think it was, yeah, with a 2.5 weight % carbon dioxide in the bulk.
No, like 40%.
2.5 in the bulk, 40% in the melt.
Because the melt sucks in all the carbon, right? Yeah.
Because the melt densities I thought you were referring to, so the gauche,
Yeah,
I think that's a carbonated basalt.
it's true, but that's all I have right now.
Okay, because the carbonatite I'd have thought would be substantially less dense.
It could be. I mean, I think the fact is you can even have the melt neutrally buoyant, but the idea was to see what they really do.
I think we're going to have to end it here.